Hello and welcome to Sigridy's webcast today. We're going to be focusing on strategies for assessing back-channel communications in high-speed SerDes designs. We'll have two presenters today. First, we have Ken Willis from Sigridy. He is a marketing manager here. And also, he'll be joined by Martin Van Ursel. Martin is a senior analog engineer with the Snowbush IP division of Genum. So we'll be going through some presentation material, then showing a demonstration of a simulation that includes back-channel communications utilizing the Snowbush IP. So with that, by way of introduction, I do want to mention that we are very interested in your questions. There is a chat window, so please, throughout the presentation, submit questions, and we'll circle back to them at the end. So with that in mind, I'll turn it over to you, Ken.
Okay. Hi, everyone. This is Ken Willis. As Leslie mentioned, product marketing manager at Sigridy, in charge of our System SI tools, together with Marcus Van Ursel from Snowbush IP, division of Genum. Marcus developed their first AMI models recently, together with Sigridy, and included an industry-first capability that we're going to talk about today in back-channel support. So this is the agenda that we're going to cover today. First, we're going to do a fairly brief IBIS AMI overview, just to give us some context in the model development. Marcus will go over the PCI Express Gen 3 characteristics that he needed to model with his AMI model kit. We'll talk about back-channel communication in general, take a quick walk through the Snowbush AMI model kit, followed by a demonstration and questions and answers. Okay, so we'll start with IBIS AMI as the backdrop. Just a couple of slides on this. One of the key things with IBIS AMI, there's a lot of focus put on the algorithmic part of the model, but there's actually two main parts to these types of models. There's a circuit part of the model and the algorithmic part of the model. The circuit part contains the I/O buffer stage. For example, here is a picture of a transmitter I/O stage. This will include information typically like the voltage swing, parasitics, and can be in SPICE subcircuit or traditional IBIS format. The algorithmic part is the part that does the equalization, the adaptive equalization functionality, and that consists of two pieces, a DLL file, which has a compiled code in it that contains the actual algorithm for the model, and also an AMI file, which is just a text file that includes the user configurable parameters that you can use to set for the DLL. And you can see down here where my cursor is a display in the tool showing some of the different parameters in that AMI file that the users can set. IBIS AMI basically has two standard interfaces in it. And it's that simple, two basic interfaces. The first one, and both of them provide the ability to model equalization that you can use in your SerDes components. The first one is AMI init, and this one is based on impulse response. So what this particular interface allows is for the tool to pass to the model the impulse response of the analog channel, the circuit part of the channel. The algorithm in the DLL will decide how it wants to filter that impulse response. It will filter it and pass the modified or filtered impulse response back to the tool for it to use in its ensuing channel simulation. So this interface is typically used for what we call one-time adaptive equalization. You see a lot of pre-emphasis and de-emphasis techniques that are modeled this way, where those transmitters have adaptive algorithms built into them to optimize and set their tap coefficients and filter settings. The second interface, which is the one that actually Marcus's models are using today, is called GetWave. And GetWave does a similar function to the first one, but instead of operating on impulse response, it operates on raw time domain waveforms, just like a real device does. the raw waveforms from the channel are passed in, for example, to the receiver DLL, and the algorithm in that DLL will decide how best to filter those waveforms real time. And then instead of passing back the modified impulse response, this type of function actually passes back the modified waveform. So, for example, in the case where you use this in a receiver model, it will pass back the equalized or modified waveforms, which can then be post-processed to generate your eye diagrams and bathtub curves and other outputs for the tool. And this type of interface is typically used for real-time adaptive equalization. We see it commonly used for DFE sorts of implementations where you require real-time signal processing and real-time adaptation of coefficients and so forth. Okay? So this is just a little background on IBIS AMI. And again, these are the two main interfaces. The second function here, AMI GetWave, is the one that was used in these particular models. IBIS AMI does not currently support back-channel communications. This capability in the Snowbush model kit can be turned on or off. If you turn it off, it will run in standard IBIS AMI mode. You can go in and set coefficients and settings in the models and run them in any IBIS AMI compliant simulator. Sigrity and Snowbush think that this back-channel support capability is important, and we will be proposing an extension to the IBIS AMI standard to include this, actually as part of the specification. And we'll be doing a presentation on this in the upcoming IBIS Summit at DesignCon first week of February. Okay, but the current IBIS AMI specification does not support back-channel at this point. Okay. The next topic we're going to cover is the PCI Express Gen 3 characteristics that were modeled in this particular model kit. And for that, I will turn that description over to Marcus.
Thank you, Ken. So as I'm sure everybody is aware, PCI Express Gen 3 is a fairly recent standard. And while the 1.0 version of the spec only came out 2 months ago, Snowbush is actually about to tape out his third iteration of the PCI Express Gen 3 PHY. And what we're going to talk about today is really the modeling work that we've done to capture the behavior of that PHY. But first, a little bit of detail on the Gen 3 specs that bring us to the modeling issues here. So as PCI Express has gone from Gen 1 to Gen 2 to Gen 3, the data rate has gone up from 2.5 to 5 and now to 8 gigabits per second. And as the data rate has gone up, the channel insertion losses have increased dramatically. Now, the PCI committee has actually defined a worst-case channel insertion loss for Gen 3 of 22 dB at the Nyquist of 4 gig. And in order to be able to work with channels with such bad performance, they've defined a minimum equalization capability that a PCI Gen 3 compliant PHY must have. And basic summary of that is on the transmit side, it has to have a 3-tap FIR filter that can give at least 9.5 dB of de-emphasis. And on the receive side, they've defined a reference design that has 6 to 12 dB of peaking in a linear equalizer as well as at least a 1-tap DFE, although the Snowbush PHY actually has 5 taps. Now, just because the channel loss can be as bad as 22 dB doesn't mean it's always going to be 22 dB. There's nothing preventing people from gluing 2 chips together and approaching something as low as 0. So you can't have just one setting that will work for everything. And this necessitates some sort of adaptation in the physical system. Now, on the RX side, this is actually fairly simple. The RX can look at the signal integrity of the signal it's seeing and analyze whether or not it needs to adjust its own settings to improve the situation. The transmit, on the other hand, is a fair bit more complicated. For the transmit to adapt, it needs to know what's going on the receive side. So there has to be some sort of back-channel mechanism to provide this adaptation. Now, just as the RX is easy and the TX is difficult in physical reality, this also holds true in the modeling world. So for an IBIS AMI model, it's fairly simple for the RX AMI model to do adaptation. It just looks at its own data and can adjust its parameters and go about its business for the adaptation. The transmit AMI model, however, needs information contained within the RX AMI model. And that's what really brings us here today. It's how do you get the TX AMI model talking to the RX AMI model? And that requires back-channel communication, and Ken will go into a little bit more detail on that now.
Thank you, Marcus. Okay, so what is back-channel communication? The definition that we're looking at for back-channel is particularly this means by which a SerDes receiver can provide some feedback to its transmitter regarding how to optimize its equalization settings for signal integrity and signal quality. So this is typically achieved by having the transmitter, before you do the data transmission, there's a training loop or a training sequence that occurs where the transmitter will send a test pattern of data to the receiver. And the receiver will look at it, take judgment on the quality of that signal, and pass back a request for adjustments to be made on the equalization of the transmitter. And this is repeated over again. So that's what we're talking about when we're discussing back channel. This is what the typical flow will look like. So if you follow, it's pretty simple. We start up here in the green box. So the transmitter will send some test pattern through the channel to the receiver. The receiver will take this and evaluate that test pattern and decide if the signal integrity or signal quality looks okay. If not, it will actually recommend some adjustments for the transmitter to make on its equalization, again, through the back channel. The transmitter will then adjust its equalization settings and send another test pattern. And this loop continues until the receiver is satisfied and the signal integrity looks okay. So once it does, that training phase or back channel phase is complete, and the transmitter has its equalization settings optimized, and then you're on to the standard serial link flow where the data transmission will occur. And that's the end, okay? So basically, the addition here is really this loop. Now the receiver and the transmitter, looking at their equalization adaptation is a little bit different. So first look at the receiver. As Marcus was saying, this is basically standard functionality in today's IBIS AMI models. You can do real-time adaptation using the getWave function. You evaluate the raw waveforms at the receiver. There's signal processing that goes on, in this case using both CTLE, continuous time linear equalizer, and also DFE, decision feedback equalization. And this is all standard IBIS AMI functionality. Nothing really new here. For the transmitter, this is where some modifications took place in this particular implementation that went above and beyond. So in this case, for the transmitter, the evaluation of the raw waveforms are still done at the receiver. Because obviously what's important here is to see what the signal quality looks like at the receiver. So the receiver is still the decision-making point. The receiver passes its information back to the transmitter on how to best modify its settings through the back channel. So again, this functionality is above and beyond standard IBIS AMI. Okay, now Marcus will walk us through a quick overview on the Snowbush AMI model kit.
Thanks, Ken. So the Snowbush AMI model kit contains all the pieces you'd expect to see in a complete IBIS delivery. Basically, we have the traditional RX and TX circuit models, the traditional IBIS files that you've been seeing for years. We also have the TX algorithmic model, the .ami file, and the DLL, and an RX AMI file and DLL. And of course, these algorithmic models have been modified to provide the back-channel support that we're discussing. And of course, we've got documentation to allow you to figure out how to use all of this good stuff. So the circuit models, as I said, are just traditional IBIS I/O models using the standard buffers defined in the standard, and they're correlated to transistor-level SPICE results to match both return loss and transient behavior. The transmit algorithmic model is actually a fairly simple beast. For the most part, it's really just a 3-tap for a filter with a little bit of added intelligence to deal with the back-channel communications. There's a whole bunch of parameters that we can tweak on this thing, but we'll go into those during the demo. On the RX side, this model is actually a fair bit more complicated. Our RX model captures the receiver in our PHY in quite good detail. It captures the front-end attenuator, the linear equalizer, 5-tap DFE, and the full CDR behavior that you'll find in our product. And it's accurate to the point that the CDR implementation in the model is actually implemented almost directly as a copy of what's in the physical part. The architectures are the same. It's not just a generic clock recovery scheme. Again, there's a whole bunch of controls in here, which we'll go into a little bit more detail during the demo. So to actually implement the back-channel support in the models, we've just slightly extended the existing standard IBIS AMI get wave function to enable some back-channel communications to be passed through parameters between the TX and RX AMI models, basically using the existing parameters out feature that's already in the models. The best way to really illustrate how the parameter passing works is to just walk you through the two AMI models and show you what the communication is that's going on here. So starting in the transmitter, when the transmit AMI model is initialized, it reads in some increment, decrement, and hold instructions or parameters that the receive AMI model has written out. It takes these parameters and then uses them to adjust the transmitter's tap coefficients, and those in turn will then be used to filter a data sequence and generate basically a time domain packet that will get sent out for the receiver to look at. When that function is finished, it closes and writes out the status of the tap coefficients, basically saying whether the taps have saturated high, saturated low, or if you're good to go and continue adaptation. In the receive model, when the receive model is initialized, it reads in the coefficient status that the TX just wrote out. It then also sucks in the filtered data packet that the transmitter generated. The receiver will analyze the signal integrity at the receive side based on what it's seeing in that data packet and come to some decision about the quality of the tap coefficients in the transmitter. And when that receive function closes, it will then write out some parameters basically saying increment tap 1, decrement tap 2, and this information gets passed out as parameters that then in turn get read by the transmitter. And then it goes back and forth. You basically go from the receiver to the transmitter to the receiver to the transmitter. The simulation alternates between these two function calls with parameters being passed back and forth between them. And what's being done on the EDA tool side is Sigridy's channel designer tool has been modified basically to just provide that interaction mechanism between the two AMI models. That's really the new element that we've introduced here, a method of taking the parameters from the TX model and the RX model and giving them to each other. Finally, the final piece of the model kit is documentation, of course. So basically we have a full document that describes all the user controllable settings within our models and block diagrams of both the TX and RX showing you how those different settings interact with the physical block and produce the expected results. So now I guess Ken will give a demonstration of how these models work.
Okay, thank you, Marcus. All right, let's take a look at the models in action. Let me just bring up the tool. I've run a couple of simulations ahead of time just to save us some time. You can see a quick look at those results here. First of all, to look at the channel, we've got the transmitter here with its circuit and algorithmic model going through a package. There's a fairly lossy channel here in the PCB block and into the receiver, where again you see in the receiver you'll have the input parasitics and the termination and the receiver algorithmic model that Marcus had described. Now the first simulation I ran was with no equalization, both the TX and RX equalization turned off, and you can see if you take a quick look at this eye is closed. So there's no opening here at all. If we look at the second result, this is with the equalization turned on, both at the transmitter and receiver, but no back channel communication. So you can start to see the makings of an eye opening, but the eye remains closed at this point. Okay? So basically no equalization turned on, but no back channel.
Yep.
And that's where we pick up. So what we'll do now is we'll go in and actually turn on the back channel capability. By flipping this particular switch to enable the transmitter to adapt. And we'll go ahead and rerun the simulation. So the model kit, as it's constituted now, prints out a lot of information to the console so that you can see, give some feedback while it's running. But you can see the back channel communication. Basically, you can see the increment, decrement, hold information flashing by as the receiver is sending information back to the transmitter. So that takes a minute to run. While that's running, what we can do is take a quick look at this S parameter for the channel.
And actually, Ken, when it's convenient, there are a couple of questions that have come in. So if there's some time while the simulation's running, maybe I can go through a couple of those.
Sure.
So one of the first questions that came in was how to obtain models. Do those come from the IP supplier?
Yeah, I mean that's the best place to obtain those models, obviously, for a particular component is from your IP supplier. The EDA tools, our EDA tool anyways, and I suspect most other ones will come with some starter set of equalization models. In Sigerty's Channel Designer, we have a full complement of FFE, DFE, CTLE sorts of equalization models that are parameterized to allow you to tailor that for a particular application or to mimic a particular IP's behavior.
Okay, and then one more question, and then I'll let you proceed. Another person wanted to know kind of how this would work if the transmitter was from one supplier and the receiver was from another supplier. Would this same kind of flow work?
Very good question. Currently, the only back channel TX and RX enabled models that we know about in the industry today are these ones here from Snowbush. As we work to get this incorporated as part of the IBIS AMI standard, what the goal is to make that part of the standard so that all IP suppliers that have back channel capability will have the means by which to enable the back channel to work. So this means that if it's incorporated as part of the standard, that you could theoretically have a transmitter from one IP supplier and a receiver from another IP supplier. Let's say they're both PCI Express Gen 3 components, and the goal of all of this is that that back channel capability will actually work between those two components.
Eventually, it should become IP independent as this gets standardized.
Okay, so we've got some initial results, and as we can see here from this result, that we actually have an eye opening now. So we've gone from no equalization, equalization on but not optimized, and this is actually with the back channel capability running. So you can see that that in this case the receiver was able to provide that feedback throughout the run to the transmitter, and the transmitter's optimization of its settings resulted in the ability to actually open up the eye. Okay, now if we look at the report, you can see the eye's still not, it doesn't have a tremendous amount of eye height here. We're at about 45 millivolts, and although open, that's still a little bit on the low side. So what I'm going to do is go into the receiver model, and I'm going to turn up the boost a little bit on the CTLE by modifying one of these parameters. We're going to change the initial CTLE boost. We'll go from 1 to 2, and we're going to rerun that. Okay, and this is running about a 250,000 bits in this simulation, so it's a pretty long simulation, but as you can see, it runs fairly quickly and allows you to do trade-offs and so forth. Okay, so circling back here to the S parameter, this is a shot of the insertion loss for the S parameter, and take a quick measurement while that's running. And again, we're going to look around the 4 gig mark. So if we sort of zoom in over here, we can see at 4 gig, looking at this insertion loss, we're at around 18.5 dB down. Okay, so it's a fairly lossy channel. And if we go back and look at the specification that we talked about here, you can see that the insertion loss can be up to 22 dB at 4 gig, and we're at about 18.5. So we're getting close. So the main message here is that we're on the fairly lossy side of things here with this particular channel. So it's a good test for the IP and for the model. Okay.
And in the last simulation that you just saw, you're getting at about 10 dB of boost on the transmit side and probably about 6 or 7 on the receive side. So what Ken has done here is now just turned up the RX side a little bit to help balance things out a little bit.
Okay. And so now as we look again, we've gone from here to here on the eye density. A little bit easier to see this maybe with the eye contours, which lets you overlay things pretty easily. You can see the pink one, the blue one is the one we had from the first back channel run. The pink one is actually, again, with the back channel, but also with the boost on the CTLE turned up a bit. So you can see there's all kinds of trade-offs and parameters to set and knobs to turn in these models per the documentation that's provided. You can also see, take a quick look at the bathtub curves. You can see the first 2 bathtub curves bottomed out because the eye closed, and the blue was with the first back channel run, and the pink was with this last one with the back channel plus, again, a little more aggressive CTLE. All right, let's go back to the presentation for a moment. Okay, so to summarize, Snowbush, the IP division of Genome, they've introduced IBIS AMI support for its PCI Express Gen 3 SerDes IP. This was their initial AMI model kit, and worked together with Sigrity in its initial development. Advanced serial link standards use back-channel communication. Standards like PCI Express Gen 3, 10G-based KR, and other emerging standards. And why is that important to simulate? It's important because it helps to accurately emulate the behavior of the hardware. Because as you saw in the real IP, the receiver is the decision point, and it's making decisions about the signal quality, and it's passing feedback to the transmitter in order to optimize its equalization settings. And obviously, how those settings get made has a huge impact on what the simulation results look like. And of course, you want that to emulate the hardware as close as possible so that you can predict what you're going to see in the lab. Sigrity and Snowbush together work to provide what I believe to be the industry's first back-channel support for these types of advanced SerDes devices. And again, our plan is to go later on this month to start the process to propose back-channel support in the IBIS AMI standard so that we can bring this capability to the entire industry. And you can have interchangeability between different IP suppliers that utilize back-channel communications for a given standard. Okay, I think at this point, Leslie, we're ready for any more questions that may have come up. Leslie, any questions from the listening audience?
Yes, actually we have a bunch of them. I put myself on mute, so I apologize for that. One person asked about changes that were made to the get wave function in IBIS. You had mentioned that you and Snowbush would be presenting some of this to the IBIS committee. Can you talk more about that?
I can touch on that one, sure. Basically, we're using the parameters out feature of the get wave. In the existing implementation, if you go by the IBIS standard, the parameters out function is only an output from the model. We've basically made that bidirectional so that you can read and write from that function, and the parameters out basically gets linked between the two models.
Okay. And then another person is asking about a point you touched on a little bit. You've certainly shown in the demonstration a simulation using Channel Designer. And one person asked, well, what if there's another vendor's simulation tool being used? We'd hate that, but it's a valid question.
In that case, I think I had covered this a little bit earlier. The back channel implementation at this point is unique to Sigrity's solution. We intend to make that part of the standard so that any EDA tool that supports IBIS AMI should be able to handle that. But of course, currently that's not the case. So what we did is, we wanted to carefully make sure that we didn't exclude the ability of customers to use whatever tools they choose to use. So in this case, they can simply turn off the back channel capability, and they can use the Snowbush AMI model kit in standard IBIS AMI mode, just like all the other SerDes models that are out there today in AMI format.
Okay, and then we also have a question from someone. Actually, this question was from two different people, slightly differently, but the gist of it is, are there any generic models that someone can work with that are available either from Sigrity or from Snowbush?
From Sigrity's standpoint, it's probably best taken offline, but Sigrity certainly would be willing to work with any other companies that are interested in implementing back channel capability. And of course, it would be great for us. We'd be looking for support as we go to the IBIS committee to make this part of the standard, and perhaps some assistance with that could occur as well.
Okay, And then there are a couple of questions that go back to the simulation itself. So one person has just asked, how do you correlate compensation settings in AMI for a given device to the actual control register bits in the part?
Marcus?
So that one would probably be for me. The way the model is currently written, most of the controls mimic quite closely what we really have in the physical part in the register that you would set. As an example, if you were to look at the settings for our transmit model, they're basically exactly the same as the pipe interface. Basically, I've put the pipe controls, the PCI Express pipe controls, as the AMI settings. So it's really a direct correlation, and it should line up fairly closely.
Okay. And another question that it looks like I missed was a person who is asking about how the back channel training is done. Is it done just one time, or is it done more than that?
In the way I've written the models currently, it basically happens during a training routine at the beginning of the simulation. It's not really, you could make it any way you want. In the existing one, it's done at the very beginning, but that's really implementation dependent.
Okay. Okay, great. Let's see, there were some questions that maybe are better handled offline. There was a person who was kind of interested in learning more about the Snowbush IP, so we'll certainly kind of make that connection. But another person wanted to know if you're planning at Snowbush to make other IP available that supports back-channel communications.
The only other one that would make sense currently really is 10G-based KR, because really that and PCI Express Gen 3 are the only two, at least that I know of, that require this currently.
Okay. And then I guess a last question is really a good one for you, Ken, and it was just to make a comment, if you would, about simulation times given channels of various complexities and with and without back-channel communication.
Okay. Well, there's really, in a channel simulation like what we're showing today, there's really two main simulation steps that take place. And this is covered in some detail in a previous webinar that I did that is still available on the Sigrity website. So I welcome anyone to go back and take a look at that if you want to see some details on the nuts and bolts of how the simulations run. But essentially there's a characterization step, which in our solution is done with SPICE circuit simulation to generate the impulse responses used by the channel simulator. Then there's the channel simulation step. So the first part, the characterization part, in this example, it takes about, 15 seconds or so. It's pretty fast. It's possible to have enormous channels with tremendously huge S parameter files and so forth, which we've had a lot of experience in running that have, S96Ps and S32Ps and so forth strung together in many different blocks. The characterization for those with SPICE takes a little bit longer, up on the order of, for very complex ones, maybe 10 minutes or so. But once the characterization process is complete, the actual channel simulation is very, very fast. What we've typically seen is on the order of a couple 100,000 bits, 250,000 bits, around maybe 10 seconds or so, something like that to simulate. With these particular models, with the back channel, we're doing some things like writing out a lot of information to the console, writing out a lot of things to some external files that take a little bit longer. These particular simulations, again, with the most advanced models that we know about in the industry, these ran 250,000 bit runs in about 2.5 or 3 minutes. So, and this is just on my laptop. This is no fancy computer. So that gives you some information about the sort of performance times that you should see.
Okay, that sounds good. Scrolling up, there were a couple of questions also that got back to this IBIS topic and an extension for back channel. So just to clarify, because it did seem like there might be some confusion on that point, the back channel communications is not now officially supported in IBIS, but it's being presented to the IBIS committee. And just to confirm, if someone has a model that has the back channel capability implemented, but they want it to run just as a pure IBIS model, they could turn that functionality off. Is that right?
Yeah, that's correct, and that's the way that the Snowbush models work. You have the ability to turn the back channel training off, and they operate just as a standard IBIS 5.0 compliant IBIS AMI model. So again, the intent is not to exclude vendors or force customers to use a particular tool or anything else. There was just no other means by which to do this back channel capability initially. And again, when you want to go and present something to IBIS and propose an extension to the standard, you almost have to have a clean working model of that ahead of time so that you have proof of concept in hand when you go for the extension. So that's the current status.
And again, the modification we did to the model is very slight. Really, the only thing we changed within the models was the getWave function, and the function call itself for the getWave has not changed. The only thing that has changed is that the pointer that was used to pass in the parameters out, that pointer can now be used to both generate output data as well as read in results as well. So we basically just made that pointer connect to a bidirectional register instead of an output-only register. But the function call itself is exactly the same, so it doesn't break anything.
Okay, and then kind of a related question. Someone else asked how the simulator, how Channel Designer distinguishes between models that support back channel simulation and those that don't.
Currently, there's only one model kit that supports back channel, so that's a very easy thing to do.
But I guess the other answer for this as well is that the way the models are currently written, there is a training file that both AMI models have to point to, and the simulator won't treat it as a valid back channel system unless they're both pointing to the same training file. That training file basically just contains information that says, this is how we want to run the back channel, here's some of the details on how to do it. But it won't be recognized as a valid system without that.
Okay, and then kind of a detailed question. Hopefully I can get this right. So someone else asked how the bit error rate is calculated at IE-12. And the question is it an empirical simulation that is then extrapolated from the 250,000 bits, or is it an analytical solution and the 250,000 bits are only used for the adaptation?
No, the way that it works is the actual raw waveforms are folded onto each other and post-processed to create that eye density that we saw in the demonstration. And from the eye density, which will then include whatever crosstalk is in the system, as well as any jitter injection that you've injected into the analysis, that eye density will be post-processed statistically using industry-standard dual Dirac methods to do the extrapolation and produce the bathtub curves.
Okay, and then another person asked a couple of moments ago, how do you correlate compensation settings in an AMI model for a given device to the actual control register bits in actual parts?
I think that one we covered already, right?
Yeah, actually, that's right. That's right, we did. Okay, so then it looks like we have just one more, and that is a person who is wanting to know a little bit more about vendors that IC suppliers that are working to create, which SerDes vendors are we working with on back channel communications. And I guess I'll just make a comment that the Snowbush IP group is our first, and I guess there's some discussions with others, but that probably is something to handle offline. Okay, good. Then I think what we'll do is leave it there. I want to thank Ken for putting the material together, and particularly thank Marcus for his involvement in working with us on this project and for participating today. And mostly thank all of you for joining us. If you have follow-on questions for us, just get in touch and we'll pursue those things individually. So thanks a lot.